Okay, so this was a problem we started to talk about the last time, that basically given us a beam, and this time says, okay, if this is a beam and this is a load, design that beam. And this is usually the way that you're gonna work with it. You have the members, whatever you're designing, and you usually know the loads applied on that member, and then you want to design it. In this case. So the very first thing that we did that is, okay, we go ahead and say, we have to draw the shear and moment diagram in order to find out what's going to be the maximum shear applying on that, what's going to be the maximum moment applying on that. If you had a beam that has the torsion or axial load, we had to draw those as well to find out what's the maximum torsion and what's the maximum axial load. Eventually, when we are designing a member, we have to check for all four these conditions, for the axial load, for the torsion, for the bending, and for the shear. So look at here, the member we are given, it doesn't have a torsion, it doesn't have the axial load. It has the transverse load, which causes the shear and bending. So we have to check it for these two. We don't need to check it for the torsion or the axial load because we don't have it. Usually, in practice, when you have the member that has the transverse load, it's not the case all the time, but usually the moment is the one that is caused the failure, not the shear. So usually, if you design it for the moment and check it for the shear, it would be fine. Not always, but usually it's the case. So when you want to design it, you have to either design it first for the shear and check it for the moment, or you have to design it for the moment and check it for the shear. As I said, in most cases, the moment is the one that defines the case. So most of the time, we start to design it for the moment, and we go back and we check it for the shear to see if it stands. As I said, if you had the axial load or the torsion, we have to check them for those as well. So I'm gonna go ahead and start to design that the member for the bending. So I'm gonna make sure that it does not fail under the bending. So first, so I'm gonna design for the bending. So the equation for the bending, what was that? The sigma was MC ion, or basically M divided by S. That was what we are using for that purpose. What was the S? S was the I divided by C for the rectangular cross section. You can memorize it, or you can always calculate it. So the I is 1/12 of the width, which is 3.5 times the height to the cube, divided by C, which is going to be half of the D. Or as I can memorize the equation or have it on your formula. So if you calculate the S would be 0.5833 d squared. So that's the for S for that problem that we have. It's gonna be. So I'm gonna put them in the equation. So I know that in that equation, the sigma allowable should be equal to M max divided by S min. So that's what I want to calculate. So the sigma allowable is 1800 psi. So the 1800 is equal to maximum moment that I have is the 90 divided by that 0.5833 d squared. So that's the minimum S that I have. So d squared would be, so the d would be, so if I do the calculation, the d would comes out as 9.26 inch. So that's the minimum depth that I can have. So my depth should be either that or larger than that. In order that it satisfies that value. Okay, so if I want to design it for bending and to make sure that it's a standing, so I'm going to say, okay, it's 3.5, it's going to be probably 9.3, the height. Or something like that. So that's, now that I design it for the bending, I have to go ahead and check it for the shear, or whatever other things that I have. As I said, if I have torsion, I have to check it for the torsion. If I have the axial load, I have to go and check it for axial load as well. Here I only have the shear, so I have to go back and check it for the shear. So I'm going and checking for shear. So I have to go and check and make sure this doesn't fail under the shear. So it's a rectangular cross section. In the rectangular cross section, what was the maximum shear stress? Remember that? In rectangular section, we had that the tau max was right. So it was the 1.5 times of the uniform shear stress. If I calculate the shear stress uniformly in the cross section, it's going to be 1.5 times of that. Remember from what we had for the rectangular cross section. So that's the maximum that's going to happen. So tau max is going to be the maximum shear is 3 divided by cross section, which is going to be 3.5 multiplied by the one that we just calculated, 9.26. So the tau max would become equal to 138.8 psi. So look at that. The tau max that happened in my cross section is going to be 138. How much is allowed? 120. So if I design it for the bending, it's going to fail under shear. As I said, usually it's not the case, but as you can look at here, so it's going to be, it is larger than that, so allowable, which is 120. So we cannot use that because it's going to fail under the shear. So now that I know it's failing under shear, if I design it for the bending, it's going to fail under shear, I have to go ahead and redesign it. So I have redesigned it for the shear. So I have to go ahead and say, if it didn't work, I have to go ahead and redesign it. For shear. So if I want to redesign it for the shear is that I know the tau max is 3/2 of V max divided by area. And then I will go ahead and say, okay, so tau max I want it to be equal to tau L. I want my maximum become that, so it's going to be tau L. It's going to be 3/2 of the V max divided by area. Therefore, 120 is going to be 3/2. V max, which is going to be 3 divided by 3.5 times D. And then the D would become, so it should comes out larger than that. So it's about 10.7. So we don't need to go ahead and recheck it for the bending because that 10 is already larger than the 9. You know that the minimum we need for the bending is the 9, and it's already larger than that. So it's gonna satisfy that as well. So this is the general, I would say, method for any given member that asks you to design it. So you have to go ahead and whatever type of force you have on that, axial, torsion, bending, and shear, these are one of these 4. You find the maximum for them, and then you start to design one of them, and you recheck for the every other cases. And if it fails, redesign it, and again recheck it until you make sure it's not failing under any of these axial load, torsion, bending, and shear. Okay. So the next topic is that I want, for this part, mostly we talk about the vertical shear stress. Now I want to see what's the longitudinal shear stress. We talked a little bit about it at the beginning, so just a little bit more about that. I'm going to draw 2 examples. The equation is the same for any of them. It's just you have to know how you actually go and use those equations. So assume I'm going to draw 2 cross sections. So assume I have one cross section look like this. So I have a cross-section look like this, and then I'm using some nail to hold it in its place. So I have some nails here, 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 So I have cross section like that made of 4 pieces. I put them together, and then I want to see how much force is going to be applied on those nails. So I want to make it look like 3D, so it's look like this. Something like that. Okay. So I want to see how much force is going to apply on those nails. So remember that any place, any time that I want to see how much force applied on the line, on any surface, I have to cut it at that surface and disassemble it from that surface. So if I want to know how much force is applying there, I have to go ahead and, for example, along that line, I'm going to cut it. So if I want to see what's happening there, I have to go ahead and say, hey, I'm going to cut it there. I'm going to cut it at that point. So I will split it at that point. For example, I'm going to call it the AA. And I will bring out either the top part or the bottom part. Remember that anytime we cut the cross section, when we want to calculate the shear for the cube, we need to keep one of the, it's easier to keep the top part of that. So if I go ahead and keep the top part, I said, okay, I will keep the top, only the top part. And this is that AA. Where the horizontal forces would be applied.
On the edges of the screw?
Yep. There and there.
Yep.
At those points. So the shear one that wants to cut it horizontally is going to be one of them there and one of them there. So I'm going to have 2 shear forces applying at that point. So in the cross section that they actually, right, so I have one here, and I have one here. So the equation to calculate the Q, the horizontal force, was what that? VQ divided by I, correct? So this and here, just for a moment, the VQ divided by I, it gives the total horizontal force on that part that I cut it off. So that is the total force on the AA. So how much is going to be each of them? Half of it. So the total Q on the AA, so total Q on the AA is this. But half of it goes to this nail, half of it goes to that nail. So it's going to be half of the Q is going to be half of the Q. No, so I'm gonna just So assume this time I have the beam look like this. And this time I have the nail going this way. So now how much force would be go on each nail? So look at here, I know that if I want to know that how much force goes on each nail, I will cut it in a way that cut the nail. Then I split it into two parts, keep the part that is easier to deal with, calculate the Q for that and see how much is there. Now how would you break that?
Cut out the middle section.
Here?
Yeah.
So if I cut it here, none of them go through the nail.
Could you cut it into thirds, basically? Slice it into a left, a middle, and a right piece.
Cut it like this.
Yeah.
So if I cut it like that, then how I'm gonna calculate the Q for that? The Q for that. So I have to cut it in a way that I can calculate the Q. So I have to have it either the top part or bottom part. So in this case, and remember that's the entire point. You don't need to cut it like that. You can cut it in any way you want. So here, I can go ahead and cut it like that. I can go there, cut it like this. I'll say, okay, that is my cutting edge. Well, let's call it BB so it's not gonna mix up with it. So I'm cutting it like that. And then if I cut it like that, what's gonna be left is that this middle part. The BB is here. So that's the B and B. Again, the Q is the same, is the VQ divided by I, the horizontal force. And this time, it's gonna be splitted where? So one of the Q is gonna be here. The other one, I can't draw it, so I'm draw it here, but it's gonna be here. And each of them, again, is gonna be, so it's gonna be a split, the horizontal force between them. As the same thing, if you end up cutting in 5 different positions, your Q is gonna be splitted in 5 different positions. Whatever number of cuts, you just split between them. So that's the entire idea how you can calculate it. So if you're asked to find the horizontal force, you have to go ahead and cut it, split it, keep one half on one part, and then just divide what the total horizontal shear stress or total shear force between any number of cut that you have. Do you get the entire idea how it works? So now let's look at an example. So we have cross section look like the second part. So if I have a cross section like this. And then it's 4.5-inch. That's 0.75. And there are the nails here. So the spacing between nails is 1.75 inch. So every 1.75 each will have one nail. The shear in the cross section is 600 pounds. So we want to know what's the shear force. Shear force on each nail. So how much shear is applied on each nail? That's what we're looking for. So similar to the previous section, if I want to know how much shear is applied on that, I have to go ahead and cut it in a way that I can bring out those nails. So I can go ahead and say, hey, I'm gonna start to cutting it like this. I will cut it like that, and then I will bring out that part. my neutral axis. That's it. Neutral axis. So I want to. The very first thing I need to calculate the Q for that area I just brought out. Correct? So the Q was, how much the Q? Is area times Y bar. Sorry. So how much is the Y bar there? Well, this is the, so from the centroid to that, so that's the Y bar, which would be, how much is that? 2.25 minus 0.75 divided by 2.
382.5.
No, it should be less than 3.
Oh.
1 point. It says it's 1.875. Because the half of it is 2.25.
Yep.
And then you get half of the 75.75 out of the 2.25. Is that correct? So that's the Y. So the error, so the Q would be, so this one is 3, this is 0.75, so it's going to be 3 times 0.75 multiplied by 1.875. I'm just gonna name that so you know that, okay, if this is the A, B, C, and E, so that's the A, B, C, and E, so you know what I'm bringing out. So that Q for that A, B, C, D is, which is about 4.22. So the Q would be 4.22 inch cube. So that's the Q that I want. Then we have, so in here we are finding Q. Then we find I. So how do I find the I for that cross section, for the entire cross section? The easy way. One way is that I go ahead and find the I for this and this and this and this and add them all together. Which is not the easy way, but let's go for it. Yeah, but how to calculate the I? Not the central. So can I say the I for the cross section, for the entire cross section, is the I of the this is the square. The I of the square or rectangle. So we'll put the rectangle, but it's not rectangle. So minus the I of the whole. So I said I of that cross section minus the I inside that. It's easier to do it that way. As I said, you can calculate the I for all four and then add them together. But as usual, it's easier to do, so it's going to be 1/12 of the B, which is 4.5 times 4.5, the height there, minus 1/12 of, for the whole, it's going to be 3.5 BH cubed, correct? BH cubed. Which here I would becomes 27.42. Again, if you get confused of that or you forget about that, you can calculate the I for all the four and add them together. Now that I have the I can go ahead and calculate the force. So we'll find Q. So Q is VQ divided by I. So the Q is V, which is 600, times the BQ, which is 4.22 divided by I, which is 27.42. So the Q would be 92.3 pound per meter. Remember that the cube is the force per unit of length. So, per inch, sorry.
Yeah, because we're mixing up our systems now.
So remember that the Q is the force, the longitudinal force per every foot or per every meter, depending on what unit we are using. There. So now that I know, so how much would be on each side?
I mean, there's so much closer.
So on each side of that, if I have that, if I draw that, I'm gonna have the half of the cube going there, the other half going there. So how much force would be applied on each nail? You know that the Q is the force divided by length. In this case, half of the Q, which is gonna be, how much would be?
46.15.
That's not it. I'm going 92.3 divided by 2 is equal to force divided by, in this thing, 1.75. I want to know how much is going to be force at every 1.75 meter. So the force would be 80.8 pounds. So that's what happening. Okay. So remember that this is the spacing between the nail. That is the spacing between nails. And this is half of the cube. So half of it goes to the left, half of it goes to the right. Or if you want to move it, so it's not gonna, because it's the cube total basically. It's the cube total is equal to that, then half of it goes here, half of it goes. Any question about any of these things? So, if you are given any problem and they ask you what is the force, usually it's like that, what's the force applying on the nail? And the force applying on the nail is the longitudinal or horizontal force applying on the nail. So you have to cut the section and bring the part that has the nail in it. So try to find a way to cut it, bring the part that has a nail in it, find the force, the total force applying on that, and then divide it to see how much each nail is to have. Any question? So the next is going to be the last topic for the shear, and basically we are going to look at it, the shear stress in the thin wall. So it's going to build on this concept that we can go ahead and if we have a nail, we're going to cut and bring out the nail. Now let's look at what if instead of having the nail there, this entire thing is one section. So I build a cross section that has a thin wall already connected to each other. How the shear works there. That's going to be very similar to this. So the shearing stress in the thin wall. So assume I have a cross section like this. Then I'm going to have that's the X. That's going to be the and that's going to be the Y. This is my coordinate system. And I say, hey, you know what? I want to know how much would be the shear stress in this section. If I go ahead and cut that section, I call it the AA. What's the shear stress on the AA? And then how much the shear stress if I cut it vertically? Here, on BB. How much would the shear stress there? So once I cut it on the AA, these two. Once I cut it on the BB, what would the shear stress there? So if I go ahead and say, hey, okay, I'm gonna once cut it on that cross section and see what happens. So this is my cross section. So if I go ahead and cut it at the AA, the top, the direction of the would be BQ divided by R. So the Q for where? The Q for this area, correct? The Q on top of where I cut it. So if I call this area A prime, so it's going to be the Q of the A prime. So now I need the T. Where would be the T? The T of that AA, which would be where? That is the T of the AA. This is vertical shear. Look at that, I cut it this way and the shear would be vertically. So that shear is pointing downward there. If I use that equation there. What if I call it at the BB? So if I go ahead and say, hey, okay, I'm gonna this time I'll cut it at the BB. This time, this area, I call it the B prime, and this is going to be the T of the BB. Again, the shear stress is the equation would be the same. The tau would be VQ divided by I T. So here is T is the AA. Here the T would be the T of the BB. The tau this time is going to be XZ. And this would be the B prime. So this time I have to calculate the Q for the B prime. That's the area. The tau would be this, the the thickness would be this, the thickness of the flange, and then it's gonna be XC, which would be horizontal shear. So look at here. So if I cut it like that, the shear look like this, is moving downward. So it's the vertical shear stress. It wants to cut it like, as I said, the butter want to cut it, it's gone. If I cut it like that, then the shear is gonna look like that. It wants to cut it this way. Okay, so you can assume the butter, if you can cut the butter like that, or you can cut the butter like that. Correct? So you can put the knife from top to the bottom, or you can put the knife and go from left to the right. So if I want to see how much the shear cutting it in this direction, I have to cut the cross section like that. If I want to see how the shear go up and down, cut it. So in other way, whatever direction I want to find the shear, I have to cut it perpendicular to that. Because that's the point, you got it? So whatever direction I look for, cut perpendicular to that. So it gives you which direction it's gonna cut that. Look at this part here. I'm gonna bring that part also. You can see that. So if I, this section, if I call it 1, 2, 3. So if I call it 1, 2, 3, and 4. I will bring that 1, 2, 3, 4 out so you can see how it's gonna look like. So if I bring that one and magnify it. So it's gonna be 1, 2, 3, and 4. If I bring that out, the shear stress on that is going to be tau xy. It's going to be tau yx. That's how those shear stress would be. If you just wonder which one is which, you can always look at that. So it gives you which one is which. Yx, xy, xe, cx. So, in other words, we can use Q equal to VQ divided by I, or tau is equal to VQ divided by IT in any section as long as cut is perpendicular to surface. So as long as we cut it perpendicular to the surface, we can use that equation. Question? concept is shear flow. So based on what we have there, how the shear actually changes the cross section. So the shear flow. And look at here. If I cut this BB very close to the edge, if it's very close to the edge, what would happen? The area would become very small. So that cube becomes very small. So basically that would be 0. If I keep moving away from that edge, so the area becomes larger and larger, so the cube becomes larger and larger, so the top becomes larger and larger. Or otherwise, the small cube becomes larger and larger. The same is here. If I cut it very close to that edge, the cube, this cube, the small cube is very small, and then it becomes larger and larger. So if you look at this problem, you'll see that it depends where I'm gonna cut it. The same here, if the AA is at the very top edge, the area is gonna be 0. And if I keep moving down and down and down, the area becomes larger and larger and larger, so the shear stress becomes larger and larger and larger. So it's very dependent where I'm gonna cut it. This is the where idea comes, mostly visually, to see how the things change. So if I have the I shape, section, if I go ahead and start to cut that section, as I said, depending on where I'm cutting it, so if I cut it here, if I cut it there, the cube would be very small, correct? It's a very small cube. If I go ahead and cut it a little bit further in, the cube would become larger. The same on the other side. So if I cut it at very close to the edge, it's going to be very small cube. If I cut it away from the edge, the cube becomes larger. So it becomes bigger and bigger the further away I will go from that. Now, if I start to cut it vertically, okay, if I cut it vertically, if I cut it here, the cube, for example, is this one. If I cut it right in the middle, it becomes the largest, correct? If I go down and again cut it here, the cube becomes smaller and smaller and smaller until I get to that edge. Agree? So if I go and draw how the cube is changing in that cross section, so if I say, okay, yes, I have that cross section drawn again. If you look at the cube, this time I'm gonna just put the arrow there. The arrows in that cross section is gonna start to move like this. So it's gonna be very small here, and then becomes larger here, become larger here, become larger, become larger, and become larger, and become largest, and larger. Then you have them going like this, like this, like this. called the shear flow. So it starts at very small, at the very edge. So at the edge is going to be 0, and the way you move away from the edge becomes larger and larger. Then again, when you move toward the edge, it becomes smaller and smaller. Can have it the same things if I'm going to do this with the rectangle. So for example, instead of having the eye, I can have the rectangle. Something like that. And then I go ahead and start to cut that part again. So this time, every time I want to cut it, I have to cut it at both sections because I want to bring out. So if I cut it here and here, I'm going to have a very small Q there. And then if I go ahead and cut it, for example, here and here, it's going to be larger Q. Then if I go ahead and cut it here and here, I'm going to get larger Q. So if I keep cutting it from the center, it becomes larger and larger and larger. So if I go ahead and draw the Q for the entire section again, so I'm going to redraw it. The Q would be like starting from here at 0 and very small here, and then it would get larger, then becomes larger, then becomes largest at the center, then it will become smaller, 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 smaller. So that's how the shear, the Q would be following. So that's the Q. That's the Q. So basically it shows you how the shear stress or the force in the cross section will change across the section. Visually you can see that, and usually you can say, okay, if you're given that, you can look at it and say, okay, where the shear is 0 and where it becomes maximum. And you know that it's always maximum when you are close to the neutral axis. One easy way to remember that is that assume you drop the water and that water flows in that cross section. Usually the shear is like that. For example, if I pour the water here, the water goes there and comes back out there. So it's one way that, probably not very scientific way, but one way that you can see how it's gonna go there. Any question? So that's the last topic that we have. I'm gonna go put, by the way, this is called the shear flow. This is the shear flow. So I'm gonna do 1 or 2 examples, see how much time we get on this part. So it's okay, if we are given the thin wall and they were asking how to calculate the shear, how we can calculate. next example is that assume we have the I-beam shape. I have an I-beam to use. .4 inch high. Thickness of here is 0.77. That's the T of the flange. It's 0.77. The T of the flange is 0.77. The I for this cross section is 394 inch, and then there is a point assumed at A. There's a point here at A. Call it A. And that point is located at 431 inch away from the edge. So we want to know that top horizontal at A. Want to know how much is that? The horizontal shear stress at the A. The B is also 50 cubes. So, if this is what I'm given and I want to know the horizontal shear stress, if this is the horizontal shear stress, it is that way, how should I cut it? Vertically. So whatever is the horizontal, we have to cut it perpendicular to that. So I have to go ahead and start and cutting it at that point. So I'm gonna cut that here. I'm cutting it at that point. And then I have to calculate everything for this area, correct? If this is the A prime, I have to calculate everything for that A prime. So the first thing that I need to do is that to find the Q. So find Q for that area of the A prime. So the Q is A Y bar. So how much is the Y bar there? So the y bar would be from the centroid of that to centroid of this. That's the y bar. So from the neutral axis to the centroid of the area I want to calculate, which would be it says it's gonna be 4.815.
Yeah, that's what I got.
So now if I go ahead and put there, so the cube, the area is 4.31 times 0.77 multiplied by 4.815. So the Q for that A prime would be 15 times 9.8 inch cube. So that's the area, that's the y bar. Now that I have find the cube, I can go ahead and find it. Shear stress to find. Tau at A. So the tau at A would be the V cubed of the A prime, I for the entire cross section, and T at point A. What's going to be the T at that point? So the tau at A would be so say 50. The Q is 15.98. The I is given 394, and the T is going to be 0.77, which the tau at A should come out as 2.63 if I have everything right. Any question? Now, in the next example, is the follow-up on that example. It says that what if I'm gonna weld a plate on the top and bottom of that I shape? Then what would be the shear stress at A? So in other words, I have the same cross section there. So I have the same cross section as I had before. Now this time I'm gonna put two plates on top of it. I'm gonna put the plate here. I put the plate here. And then I weld them at these points. So I weld them here. I weld them here. It's welded here. It's welded here. So that's all good. So it's welded at those 4 points. And the point A is still where it was before. It's the same as the point A. Now if I weld them there, how much would the shear stress? It goes on this. That's it. 0.7 by 12 inch, so it's 0.7 height. The rest of the dimension is the same as what we had before, so it's going to be from here. So this middle part is 10.4. So this is 0.7. 5. It's 0.7. It's 0.75, not 0.7. And again, this is 0.77. So now, how much would be the shear stress at that point? So how do you cut it this time?
Are we still looking for a horizontal shear?
Yes, the same things there. The same formation we have. The eye for the beam is the same as 394. The V is that 50 keeps, and the tau at 8. How much is it? So how you are going to cut that?
Would we go for like almost a C? We cut through that top right weld, and then
Start from where?
like we cut through that top right weld going horizontally, and then we go down through A and then go back to the right, so that way we go through the joint.
And how do I deal with the weld? So I know that I have to cut through the A. So that part I know, correct? So that part I know, that I have to cut through the A. So either I have to go this way or that way. What if I go the other way? What if I go here and cut it there? What if I cut it like that? So if I cut it like that, what's gonna come out is gonna be the top of the beam, or the plate, and then I have this part, I have this part, correct? And this is the point A sitting there. This is the A. So, in that case, I don't need to deal with the welding or anything. So, okay, cut it and bring it up like that. So if I cut it and bring it like that dimension I have, so I know that this is 4.31, so this is going to be 4.31, this is going to be 4.77, this is going to be 4, this is going to be 0.75, and this is going to be 12. The same there, so it's going to be 4.31. So a couple of things I have to find for that. As soon as you learn, as soon as you get where to cut it, the rest is not much difficult. So you have to find the Q and the I for this cross section. So let's start to find. So first is a start to find the I. Let's just start to find the I.
We already know the I?
We know the I for the I shape, but we don't know it for the entire cross section.
Okay.
So find I. So the I would be I of the beam plus 2 times of the I of the, so I have 2 plates, so I of the beam plus 2 I for the plates. So I for the beam, I know that I for the beam is 394. I for the plate, for one of them, is 1/12 of the B is 12 times H, which is going to be 0.75. So plus the 80 is square, correct? Because it's away from the central, so I have to calculate it. If this is the centroid, and if this is the centroid for that, so this distance is how much? It's 5.575. times 5.575 squared. So I'm just gonna write it. So this one is 1/12 of BHQ, and this part is A, and this part is D squared. Remember when we were calculating the moment for the moment of inertia for area that is its centroid is not on the centroid of the cross section, so we have to add the AD squared at the end of that. So if I put these together,
we need to double the 112 BH cubed for the I plate. Oh wait, no.
but it's just for one of them. Yeah, you're right.
Yeah.
So I for one plate would be I don't have to. 280.14. I don't have it in. So 394 plus 2 times 280.14 will come out to 954. Is that right? So that's the I. So I know the I. Then the next thing is that I have to go ahead and find it. So remember that C is also going to go all the way to the right. That's where it's that. So then I have to find the Q. So again, the Q is going to be for the flanges and the top plate. So I have the Q. The Q is the 2 times of the Q for the flanges plus the Q for the top plate, basically. How much the Q for the flanges? The 2 times of the area by y bar, correct? 2 times the area is 4.31 times 0.77 multiplied by the y bar, which the y bar for again here. So this distance is 4.815. So that's the y bar 1, that's the y bar 2, which would be 5.575. So it's going to be multiplied by 4.815 plus the area of test, which is 12 times 0.75 multiplied by 5.75. So that's the area for flange. That's the y bar 1. So that's the area for the plate, and that's the y bar 2. So the Q eventually becomes equal to 82.1 inch cube.
You said the y bar was 5.575, and but you wrote 5.75 at the same time, so I don't.
Yeah, all right. 5.575, yes. Thank you.
And then, so even though that the plate adds height, since it's a separate thing, we don't adjust y bar for A. Oh wait, no, because y, it doesn't matter that it's a different, never mind. That was,
You have to calculate for this area and then for that
Yeah.
area separately.
once I said it out loud.
And then when I have the Q and I, then I can find the shear. So the tau would be VQ divided by I divided by T, so the tau A would be 50 times the Q, which would be 82.1 divided by I, which is 954 times the T, which would be 0.77. So the tau, the A would be 2.79. Sorry. Here, how much would be the T?
Would the thickness be 0.77 plus 0.75?
No.
Oh,
Look at how we cut it.
I did it.
So it's gonna be multiplied by 2 times 0.77. Because we cut it 2 times. So we cut it once going up and then once going down. So we cut it 2 times. So it's going to be 2 of that 0.77. Any question?